Okay, let's see if this works. Throw a name. Good. That. Good.
All of them except number 3.
Okay. You want feedback on them, or you want to finish through?
Finish 3.
Okay. Finish through. Oh, yeah. We were. Okay. And then Zori, I talked to, so David is the only one. Should stand at the window, just staring. Yeah. All right. So today we are going to continue our discussion of dynamics, but I think we need to do like a review and make sure that we're all on the same page. Folks who haven't taken 3200, which is classical mechanics, are going to feel at a disadvantage. You started it like 3200, that's great. A lot of the concepts that we'll use are your introductory physics concepts and then just elevated. So we're going to see different applications of them. What I'm going to try and do today is we'll talk about, uniform circular motion, center of mass. We'll go over the elliptical orbits. We'll do Kepler's law. This is like basically an entire review of dynamics just to make sure that when we see it at this higher level, that we're not underwater. Okay. Here's the Earth, very high resolution image satellite motion. Okay. So let's start with the beginning. Classic. Sir? All right. What are Newton's laws of motion, by the way? Yes. Good. 4. Good. Next one. You tell me. I've never worked here before.
Yeah.
Okay. Okay. What does that mean? What does that mean? Words. So there's a product there. It's also a vector quantity. But the acceleration doesn't have to be speeding up, it can be changing direction. Right? Another way of saying this is accelerations are only due to forces and they're hindered by mass. So another way of writing it would be A is F over M. And of course, you can define force this way too. Force is defined as the product of the mass and the acceleration. But intuitively, we should say that forces and acceleration are proportional directly. And they are moderated by mass. Saying F equals ma is perfectly acceptable. That's always an okay answer. But when I want to talk about, is this working? Why is this not fucking? I'm gonna murder this thing. Hello? Okay, good. Force and acceleration of vectors. Why is this doing this to me? What's the third law? Good. There we go. We got it. The 10 takes force to change the body's velocity. Whether that's in magnitude or direction. The rate at which the body changes its velocity is proportional to the force, moderated by. Good. Every force is opposed by an equal and opposite force. Or you could say, another way of saying that every force produces. This is the worst. I don't understand why this is not working. Let me try this again. End show. New show. There we go. Let's go. All right. So here's the gravitational potential and the force. And I have some extra letters. This is the force of 1 on 2. Right? That's 1, that's 2. Here's that's 1, here's that's 2. So the force of 1 on 2 pulls 2 to 1. And similarly, the force of 2 on 1 pulls 1 to 2. They are equal and opposite. That's the third law, right? Okay. You have all these numbers, don't memorize them. And we already know that. Sorry. How do you get that? This one, we're going to call Newton's gravitational law. How do I get the energy?
You have to integrate the force, right?
Good. I had to do that. So integral force.
And you got ODL.
You got it. Right. And in this case, I'm just going to go ahead. DL is correct, but I'm going to go ahead and use the coordinate system that we have here. This is going to be DR. Okay. So what we'll do is we'll take a little object here. We'll call that M1, and we'll think about some location R away. Okay. And of course, DR would be a little piece of this. Right? And so we'll have to do an integral. And we're going to integrate f dot dr, and f is in the direction of dr, so that's really trivial. So those dot products are just 1. And it's f dot dr. We can do that pretty simply over there, right? Because the g and m go out. And really what you're looking at is your integration bounds. So what's the integration bounds? Well, in this case, we don't have R1, R2. I'm just thinking about the gravitational potential energy. This one's a little trickier. The distance between them is R1 to R2. So you're just going to start at 0 and go to R1 to R2. That's the gravitational potential between them. Right? So you have to choose your bounds. And that's something I can talk about in a little bit more detail when we're looking at most problems that ask you to evaluate something. When you do an integral like this, you're always going to have an integration constant if you have unbounded integrals. So to get something really nice and beautiful like this, you have to use the integration. Okay, and this is a fun point. This is something that you noticed right away. If you have a sphere, it's perfectly spherical, it behaves like all of the mass is concentrated at a point. Okay. You can prove that. You can look at C part here, and you can add up the contributions from all of these different parts. And it looks only crazy. and all those masses. Because as long as it's uniformly spherical, then the pull from here is balanced with the pull from here. Right? Okay. So by inspection, you can do that, but you can do that with magnets. Good. Let's go around in a circle. Okay. All right. An object goes around in a circle at a constant speed. I want you to think about the canonical example that you learned in 2500. It should be a ball on a string. How do you get it to keep going in a circle? Go to move your arm. Yeah, this is going to slow down. Good. And you've got to keep tension in that wire. So let's say you get it speeding up. You get something speeded up really fast, as long as you're holding that wire taut. But if you let go at any moment, what happens?
You're in the 90-degree direction.
Good. So let's look at that really quickly. I don't have clickers, but you know this clicker question. Okay. Here's the spherical motion. Here's the tension. Here's the ball. Don't use your fingers. A being 1, B being 2, C being 3. Which direction? Traveling this way. If I let go when the ball is here, which direction does it go after? Remains in motion. So as soon as you let go, it's no longer being acted on by any force, and it heads straight instead of right. Good. All right. All right, this is working. Getting these parts. What's the acceleration here? If you're moving, what if you switch? Right? Say that again.
I was thinking 0 if it was like constant velocity.
So if it's constant velocity, that would mean that it is not changing direction. If it's constant speed, yes, I would agree with you. So going around in a circle at a constant speed, right, is different than going and changing your direction constantly. That's why the vector quantity is so important to point out there, right? So in the same way, you're 100% right. The velocity vector magnitude stays the same, but it's always changing. So therefore, to change the components, dy and dx, right? Going up and down, and up and down, and up and down, that requires force. Good. Come on. Yeah. Let's do one more thing here. We can look at the math. We can write some words. This is an angular, or this is an angle. So angular here. Angular speed is an omega as opposed to v. T is time, like we always do. And we can relate these just by saying this piece here is the velocity that you're going divided by how far away you are. That's how you define the velocity, right? So let's find the acceleration by math. Okay. And you can do this here. You can break it into components. You can say, oh, this angle is what I'm subtending in a certain amount of time. That's the product of my angular frequency times the time. So if I wait 10 seconds, maybe I get this far. If I wait 20 seconds, maybe I get that far. Right? And of course, if it's uniform circular motion, we can describe it with sines and cosines. It's trigonometric, it's periodic. We love those functions. They're really great for describing anything that's periodic. And so all I have to do is I have to go in here and say that I can break down the components of my velocity vector v into the x and y components. Right? And as I do that, I say it's cosine of something. You might call that theta to start with. Think about it a little harder. You can relate theta or eta omega t plus pi over 2. By the pi over 2, that's just simply how we're defining it. Right? So if I think about this angle here, right, that's the angle omega, or sorry, eta. But in order to see that over here, you can add 2. This is situation. Okay, so that's perfectly good. That just changed cosine to minus sine and sine to cosine. That's how we defined it. And we can take a derivative. We're really good at taking derivatives. We love doing it at home. Maybe when we get home, we just do derivatives because we're bored. So we take a time derivative, and of course, the derivative of sine is cosine. Good. You don't add an extra negative there, so that comes along. The derivative of cosine is
Negative sine.
sine. And now look, there they work, right? So we can get the amplitude A by adding the components in quadrature. This is the definition of adding in quadrature. You want the magnitude of a vector, you square them, and you add them, and then you take the square root. So this is the magnitude, and it turns out just to be omega, our friend from before, times v. But of course, we defined omega as v over r, didn't we? So we can define this as v squared over r. And now you've derived centrifugal acceleration. Anything that goes in a circle at constant speed must have this. Good. And if you want the vector formula, it's here. It's this piece and this piece. Just add our little. But then anything weird? No. And notice this is a funny one. What direction is A pointing? Inward, and R is pointing. A convention. So they're pointing in opposite directions, but of course they're aligned. Um, so this, of course, requires a force. If I have an acceleration, so that's going to be provided by the tension in the string. If it's gravity, it's provided by the tension between those two bodies, right? As a tension and force. And so we can also describe things like the period. So for example, all of the things that we're talking about now were discussed by Galileo, right? Galileo's laws of motion did not consider forces. We didn't think about them as forces. We thought about them in terms of accelerations, that they knew that there was positions and rates of change. And of course, there's full discussions about things like what is the period of the Earth? How long does it take to go around one circle? Right? So you define something like a period. You say if I go around in one whole thing, well, then that should be, right, how far you went by r divided by how long it took you to do it. But I can write this thing. This is the inverse of that thing. So if you have the angular frequency, how long it takes for you to go a certain amount of the distance in angle, then you just take 2 pi and you divide it by that. Okay? This is a really handy-dandy relationship because you often will get period of the object and you want the angular frequency. You just go ahead and simple. Okay, so now we get to the part where now you probably have Newton and some folks like that thinking about how you actually want to do this and apply this to systems. So you say that there's an equivalence between these 2 types of forces. Centrifugal acceleration that pulls you inward, and of course the gravitational potential, or so the gravitational force. So here we're doing the same thing that we did before. We have the force from gravity, we have the force from centrifugal acceleration. And this, by definition, gives you the speed. Gives you the speed that you have to go around a body where the only force is being pulled in. So we can rearrange this one and this one for v. And that's the orbital velocity. Doesn't depend on the body. only depends on the form asset. What's the total energy? Well, we like this. Familiar with this formalism? K for kinetic, U for potential. So K, we have 1/2 mv squared. It's a positive quantity. U, we already showed, is a negative quantity. Okay, so what's the total energy in the system? What's the total energy in the system? I didn't get that. Right, so what you're saying here is the potential energy is minus Gm over R, right? The kinetic energy subtract them, right? One of them is 1/2 of it. If I look at this, let's say E is equal to K plus U. And I look, not from this line here, but from this line here, I can take out the Gm over R squared, right? G m little m over R. And the first term is 1/2. And the second term is 1. Is it not? So that equals minus 1/2 G little m big M over R. And that is by definition U. Minus 1/2 U. For a bound system in circular orbit. Does that make sense? Conceptually, no. And mathematically, yes. You can follow all the algebra, but you don't get why. Let's try an example. Here. Good. Okay. put a ball right here. What energy does the ball have? Let's assume this is zero. Comments on my drawing. Oh, okay. There we go. Is that better? Here's the ball.
That's cool.
Full. There's no potential, right? There's the bottom of the hill. No potential. Is that correct?
Let's make one.
What is potential energy?
When it's like energy, but it's not movement, but it's not motion.
So potential energy doesn't have to be not in motion. Potential energy means it has a source of energy that it could be converted into other forms. So it's stored energy. So for example,
I was going to say, so would it only be potential if it's on the top, but then once it goes down, is it all then kinetic?
right? So if I put the ball up here and it's not moving, right, then it has a certain amount of stored possible energy, but it can't use that, right? I have to pick it up, bring it to the edge, hold it, and then drop it. And then it can convert all of its potential energy into motion. Okay. So down here has nothing. If I kick the ball, I give it a little kick, goes over here. What happens next? It turns around and comes back up. I kick it harder. Go all the way up to here. Goes back down faster, right? We're assuming everything's friction, right? The imaginary chalkboard. Good. I kick it super hard. It goes all the way up here and it stops. Still come back down, right? Still come down to zero. These are examples of bound motion. This ball is bound within the system. If I can kick it super far, right? If I can kick it out here, then what happens?
So land up the hill.
Well, the hill, and it'll stay up at that new hill level, right? Okay. So in one of these two circumstances, the total energy was positive, and in the other, the total energy was negative. Bound systems display negative energy because the total amount of energy is less than the necessary balance to get it to be removed from the system. They're exactly equal. The system is just enough energy to be unbound. If you have more kinetic energy than potential energy, then the system is certainly unbound, right? So here I had more kinetic energy that flew out than was necessary to keep it in the hole. Here, I didn't give it enough kinetic energy and it stayed in the hole, right? This is an example that you can use in quantum mechanics, where you have an electron that's in some potential, right? The energies of those systems are likewise negative if they're bound, right? And you give the object enough energy in the form of light, in the form of any sort of radiation that can interact with the electron, you're going to move up a level, still bound, right? You're going to find all the bound states. You have enough energy, you sometimes jump out of the well. Make sense? This is the same form that we have here, except gravitational potential. Make sense? Okay. So we need this. There's a name for this theorem. You'll learn about it in 3200. I hope. Okay. That's the energy of the system. It's negative if it's bound. If I can give the system more energy, it does not become more bound. It becomes less bound. If I take energy away from the system, it does. It's more bound. And this is a very counterintuitive result. Which system has more energy? Mercury goes around the sun very fast, something like 4 months, or Mars, which goes around the sun very slowly at something like 2 years. Mars has more energy than Mercury. Now remember, it's only orbital energy. Not taking into account the fact that it's blazing hot near the sun, right? So the way that you think about that, you still need to draw these same pictures, okay? You need to draw in your mind's eye a well, okay? If you go too close to the sun, okay? Oh, Mercury is down here. It's up here. Say to yourself, fuck this money. 1 over r doesn't go down. 1 over r goes to infinity, right? Or it's negative. This is minus infinity. Because the gravitational potential energy, U, is negative magnitude. These are bound states. And by the time that I get all the way up to here towards 0, let's see, soldiers. Out here, Jupiter. And remember, I did this whole thing about, well, you have a little planet. Say you take the Earth from Mars. That, right? You have a big old planet. Let's say you have a Mondo. That. This needs to be internalized. So you have misunderstandings about how to do this now. But later starts with some. Okay. Good. And let's go back to torque because I think this one maybe is a little bit that's also counterintuitive. Let's just think about that for a moment. We have some definitions here. In the circular motion, you have R, which is the radial piece, and V, which is the part where you're going around. So their cross product is by definition. What is their, think about this for a second. Let's draw the picture, you can see it. R, where's V?
Goes around.
Yeah, so it's going this way. Same picture that we have. Where's V? At this point right here. Yeah. So we're talking about the out, right? Verify. Okay, so where's the torque? Torque's coming in. Very good that I drew a little dot, and that's my arrow. And remember, what does this torque dot mean? The dot means coming out like an arrow, stabbing in the eye.
So the cross is
Awesome. Or yeah, this. And so this is into the board. And what's the rotation like? Clockwise, and this one's. Okay. And that's all true, right? You can see that. Good. So this cross product is sine pi over 2, but that's silly because that's 1. So we can just take R, M, and V, R, M, and V, and it's in the Z direction. That's the only thing we're saying. Z is out of them. Good. And so we're almost there. Now I have a definition for V. Right? It's right there. And I have an R, so I can put the R into my V. Gives me 2 copies, and one of them gets deleted by the R underneath. So have a look here. Oh, this is very interesting. Remember, we had some difficulty thinking about the angular momentum. Because as you get closer to the body, you move faster. And we were like, well, which one of those two wins out? Which one of those two is more important? Because if you just look at L, right? And I'm just going to do the magnitude here, which is mvr. Okay? So I'm not going to change the mass of the body, but if I decrease the radius, right, make this smaller, this should go up. Okay. That's only if it's conserved, right? I can trade the amount of L for a different amount of L in tidal walking. I can get rid of this L, right? So this has to be conserved in situations where you can't get rid of the L, where any decrease in V equals an increase in R and vice versa. So if I'm a ballerina and I bring my arms in, I decrease R and V goes up. But if I can trade my angular momentum with someone else, then these are allowed to change, right? And they still have to follow circular motion. Okay, so this helps me understand that L really is only proportional to R. And in particular, the magnitude of L for circular motion is proportional to the square root of R, if nothing else changes. So as I head farther out, the most important thing is how far I am away in determining my angular momentum. Right? So we were talking about, for example, the Earth rotating, moon rotating, and it's moving away. Okay? That process of moving away and changing your angular momentum going up, this goes up because this goes up. Right?
As a result, velocity goes up too.
Well, think about it this way. Velocity is not going up. It's still in circular motion. What can possibly make the angular momentum go up for the moon? The Earth's angular momentum has to go down. Right? So the Earth starts slowing down, and therefore the moon moves away. You see the trade-off now? It's not a trade-off between internal parts. It's a trade-off between its neighbor. So the Earth slows down and then moves. That makes sense? Now you're being experts in the brain, right? Okay. That's all I'm going to do on the circular motion. Let's do a little bit on center of mass, because we'll have to think about this when we think about it in terms of like 2-body, 3-body problems, okay? So if the masses are not very different, like for example, Pluto and Charon, the center of mass will be in between the bodies. For the Earth-Moon system, the center of mass is inside of the Earth. For the Sun, Jupiter system, it's a little bit outside the Sun. So the Sun does walk. That's how we do exoplanets, right? Okay. So center of mass is defined according to momentum conservation. And this is really important because when you think about the Earth-Moon system, even in the Earth-Moon system, the center of mass is not going to be changing, right? If they move away from each other, they have to move away from each other proportionally, so that the center of mass stays in that same location. And it's quite helpful, of course, if you think about only 2 bodies, to go into the center of mass's frame of reference. Because if everything is rotating about the center of mass, if I put the origin at the center of mass, I put one body here and one body here, and then I rotate in that same rotation, now they just fit. And it's the frame that's doing the rotating. And we can, of course, think about the rotating frame. We can introduce centrifugal terms to make up for that. But those are a lot easier to see, even when you think about them in terms of a computer, because all you have to add is something that looks like plus omega r squared to your moments, to your equations. That's not super hard to calculate. You have a centrifugal term, you have a centrifugal term. Is that all? Okay. So here's how you do it. You make a statement that the sum of the masses times the center of mass, the location of the center of mass, that should not change. Right? So we don't want that center of mass to be moving with the system. And if you've chosen the center of mass incorrectly, this derivative will not be zero. Okay? So you can, of course, write that out, apply this inwards. And what you'll do here is you will do a integration. Integrate that to get the constant. And you have a relationship between the two masses, their relative radii with respect to the origin, and the thing that you want to find, which is the center of mass. So the center of mass is a weighted average. This is the way that you want to think about it. It is the radius 1 plus radius 2 weighted by their masses divided by the sum of them. Let's imagine the first one. Let's take the simplest example. In our heads, we should be able to know this one. If the mass of one of them is m and the mass of the other one is 0, where do you expect the center of mass to be? Center of m, by definition, you would think there would be no reason to pull it away. Is that true? So let's take m equals m, and this equals 0. So this contributes nothing. This contributes nothing down here, and it's just m. Oh, interesting. It's the center of m. Or sorry, center of the one that we called 1. R1. Good. All right. Let's do the next one. Let's imagine that they are equal mass. Now, where do we expect the center of mass to develop? Or halfway between, right? We would expect that. Does this give you that property? So if M1 is M and M2 is also M, good. And R1, M1 is M and M, so this is now what? 2M, good. So this would be M plus M, so we can factor that out over 2M. Those m's cancel, it's 1/2. So it's 1/2 the distance. Remember that these are vector quantities. So these vector quantities are really important. We need to write them as vector quantities in order for any of this to make sense. So let's take mass 1 and let's take mass 2. Okay. Where is the center of mass? Just intuitively, they're equal in the situation we just said. Halfway. So we can do a little, right there is where we expect it to be. But if you just looked at R1 and R2 there, you might say to yourself, wait, what the fuck? That doesn't make any sense. Where is R1 with respect to? That's with respect to where your coordinate system is set up. Okay. So you define the coordinate system, and you have a vector here, which is R1. The distance from the origin. And then this one is let's imagine that straight, R2. Okay. And of course, this is the vector quantity, R1. R1. Okay, we're going to use that. Yeah, sorry, I forgot to say, set that constant equal to 0. Okay, unless you want to move here. The math will still work. You just don't want to. I'm saying anything different here. Yeah, so let's say those two masses here, I'm just going to call R1 plus R2. I'm going to call that R now. And I'm going to write this better. So and that way I can place the center of mass here. I'm going to shift this forward or this. But in that new coordinate system, the origin is 0. So R, C, M equals 0. And so I can rewrite that to say where R1 is and where R2 is in my new coordinate system. Similarly, we're probably going to use this. So this is worth a definition. You can define this thing. This is called the reduced mass. So in a system where you have a center of mass, you, instead of thinking about each mass individually, M1 and M2, just use mu, right? That makes it easier to keep track of. Just the only thing to be careful with, of course, is don't confuse it with other mu's, like magnetic moment mu. That's not. So you've seen effective gravity already. That's the G effective. This is essentially the reduced mass. We call this reduced mass because it's the mass in the frame that is centered on it. Let's see if it works. If M1 is M and M2 is 0, what do I get? 0. And good. If they're equal, 1, 1. Yeah, just the mass, right? So if they're equal and you're halfway in between, both of them just act like one mass. If one is more massive than the other, then it reduces the system and shifts the mass. Right? You shift the origin towards the center, and you treat the little thing that's far away as the mass in question. Does that mental exercise make sense? So just think of it like a sliding scale. The most they can ever be is equal. The least they can ever be is one is much larger than the other. Because otherwise you're just sliding back to the side. C'est bon? All right. Okay, so we can redefine those equations of motion. We can take R1 and R2, right? And we can write them in terms of the reduced mass and R. So we just have one variable for distance. So now you have the reduced mass divided by M1 indicates that I'm talking about R1. And similarly, for the second object. So I have the reduced mass divided by M2 tells me that I'm talking about the second object. Well, this turns out to be really nice because now we can go through our process of finding out what the relative velocities are. Here, right, it's just the time derivative of R1, sorry, of R, with the stuff that came with it. This is the stuff that we brought along with the definition. And now I take the rate of change of the radius. And we can call that V. Now V2, similarly, is the reduced mass divided by M2 times some central V, right? And this is the great part. Now I can talk about energies of both of these objects in terms of one V out. So here's the kinetic energy of the first object. Here's the kinetic energy of the second object. And of course, the distance between them. What's this thing here? The magnitude, so which was it in terms of what we called things before? R, exactly right. And we defined it for that reason, for simplification. So this is great. So this already simplifies. And these two, they simplify down to this. Their relative kinetic energies are just like an object with reduced mass of mu moving at some frame velocity, right? And this is almost exactly the same. You add their masses together and you multiply by some reduced mass. Okay. So in this case, right, the motion of one of the two bodies is like one of them's at rest and the other has reduced mass. That's super helpful. Because instead of having 3 terms, I just have to keep track of 2. If you wanted to do a simulation of 2 bodies, you're going to want to use this, right? Better to only simulate the motion of one of them. Leave the bigger body at home, simulate the motion of the smaller body. Does that make sense? Okay. We like it? We trust it? Okay. Okay, let's do an example. Oh no, I hate examples for fun. Describe the orbits of 2 masses M1 and M2 around the common center mass separation is R. Right? How does the force appear? Well, we just use this one, F2. That's the gravitational force in the R direction. And we have something like A2. That's okay. So this one here, V2, the velocity, orbital velocity of the second one, is Gm over R. The same thing that we had before, but of course M1 is the other body. Circular motion. How does this change in a coordinate system with the origin as the center mass? We can use these same things below. We use all of this that we just described before. But now V1, okay, is going to be related to this thing here. Are there too many steps at once, or can you do that? What do you mean opposite?
If the masses were the same.
R1 and R2, they are related, right? You know, there's gonna be some distance between them. They'll be equal and opposite in length, right? So, you know, as this one gets bigger, the other one gets longer, and so on and so forth. So they're gonna track one another. This one here, what I'm asking is the velocity 1, we can of course write in terms of velocity 2. See why that is? So let's remember what we're talking about here. We have 2 masses separated by R. They're both going around one another with, you know, for example, let's say they're both attracted, both moving in circular motion. Okay. Whether this one's doing a little circle like that, but this one's doing a big circle, either way, they're going around each other exactly around the center of motion, both moving in circular motion. So we talked about the forces here. This is the gravitational force. We can write this in terms of centripetal acceleration. Just like we had before, the velocity here is this. But this one, dr dt, if I go over here, I think dr dt is me v2. So here's a way to connect v1 and v2 simply to the distance between them, where the only thing that changes here is that the mass 1 and mass 2 are swapping, And the velocities need to, at all times, V1, that's right, V1 and V2 are going to be opposite of the sign. Right? So whichever way one is going, the other has to be going in the other direction for circular motion to serve here. Is that fair? Okay. I might be going a little too slow here. So if it's too much, let me know. If it's not enough, let me know as well. We can go back over this. So each is traveling in a circular orbit, right? They have some radius R1, which is moderated by their mass. And the speed is, of course, also moderated by their mass. So we can imagine, let's go back here and think about what if they were the same? M1's M2, right? Then we would expect both of them to be equidistant. And how should their speeds compare? Does one have a bigger speed than the other? No, let's say they're the same. Say we have two masses, both of size m. They should be the same, right? So we expect them to be the same distance apart from the center of mass, and we would have no reason to suspect that their masses wouldn't be the same, right? Let's see if that's true based on these things that we created. So here's R, m over n. Okay, so R is 1/2. Okay, did that. That was easy. Okay, this one here, V is m over 2m. Remember, that's the reduced mass here. So that makes 2 on the bottom and 1 on the top. They cancel the m's out. It's 1/2 g m over 1. That's equal. Right? Talk about escape really quickly. We were talking about things being bound, right? So this is the idea of bound energy, and I told you an example of some initial amount of energy here, where the thing is negative g m over r. That's what I wrote. Hold on. Clarify one thing. In this example, it's not a circular system. The 1/2 mv squared is 0. But imagine you have no kinetic energy in the system. You just have a ball. Okay? Something is attracted. Okay. And then you give it enough energy. 1/2 mv squared. Right? Then if you relate this energy to that energy, right? Final energy is being 0. Initial energy is being negative. That's the difference necessary to get the 2 GM, right? And this is hopefully a result that you saw. That's right. Did you see that in front of you? Did you think that up? Years ago. But you know where that book is. Oh, it's in your room. Crack it. Get the dust off. Undo the pages. Okay. So this derivation is not horrible, right? It's the same type of thing that I showed you with the drawing down here. Ball starts at the bottom, only potential energy. How do you kick it to give it enough energy to exactly escape? And the derivation there really is just talking about what's the minimum speed necessary to get this thing to leave. Because let's say this is, for Earth, it's like 50-something kilometers. So if I had an object and I clocked it at going 60 kilometers per second, then you know the thing was not coming back. If I clock it and it's doing 48, that's a pretty good chance that that's an orbit. It's a very tenuous orbit, right? Small and manageable. Send it off to oblivion. Make sense? Okay. Okay, let's talk about ellipses. Look at this version of the ellipse, came out much better. This is what I attempted to draw. See them? These are the F1, F2, C, V, A. This is how you draw it. So you have some string, and you put thin thumbtacks, and you draw the triangle. That's a piece of string. And then you put the pen here, and the string will stay taut. between these two. And that gives you the shape of it. Okay, we talked about how this is the equation, x squared over a squared plus y squared over b squared equals 1. And you can draw each of those components out there. We talked about how to find the foci. It's a squared minus b squared. If that's true, this is this length. This is the right triangle, the hypotenuse. Okay, that kind of makes sense, right? This hypotenuse also happens to be that long. Fun property of ellipses. If you do that, that allows you to open up this whole fun world, because I showed you before that eccentricity, I just sort of stated without an explanation, is C over A. You know, if you want to, you can pull out a geometry book and you can show that yourself. But if you do that, you can write eccentricity as just A and B, more or less. More importantly, you can write the focal lengths, which one can think of, the focal length here, as A plus minus C, which is the perihelion distance. Remember here, this is A, smaller of the two F's, this is the perihelion, and this would be the aphelion here. So you can just find that A is the semi-major axis, the long axis. And if the eccentricity is 0, then the distance is the same the whole time. For the perihelion distance, it's 1 minus the eccentricity. So if you have a large eccentricity, then your perihelion distance is smaller than, as opposed to the aphelion, the one where you're away, it's 1 plus E, or epsilon.
Questions about these definitions?
Okay, we're getting there. I'll say this again, said this a million times. A is three major axes, not acceleration. That was fun, right? What have I written? Okay, so as you go around the ellipse, remember before we were going around the circle, we used eta to describe the angle. So here, you're going to have two things changing. R is going to increase and decrease, and eta is going to change. So eta starts at 0, I'm going to head out towards aphelion, and then I'm going to come back in, and once eta gets to 360, I've done one orbit. But now R is going to increase. So if I want to think about this in terms of polar coordinates, I have x prime and y prime, which is just the description here, right? With respect to, I'm going to put the center of mass, by the way, I'm going to put the center of my coordinate system, I'm going to put it at the thing that I'm orbiting, right? And so this is going to be x prime, and this is y prime, as opposed to the center of the picture. Okay, so this is the perihelion distance, and I really want to understand how x prime and y prime are changing throughout the course of the orbit. Well, it's actually not horrifying, right? That's kind of what you would think for a circle, right? The only thing is this R is going to change as a function of time. We have to remember that when we do any sort of derivatives. Not only is eta changing, R is changing, right? And we can, of course, turn this, you know, we can write this with all of these pieces. This will be the change from the x squared plus y squared. We just shifted it over. Okay. Here's how you write it. This is how R is changing. So at every location in the orbit, you know, if I tell you it's about pi over 2 in an angle, so that would be this distance right here, you can figure it out based on these values. Now, is this garbage? Let's see. This should reduce to a circle if the eccentricity is 0. Does it? 1 minus 0 is 1. So A times 1 is good. 1 plus 0 is 1. So R stays A. Okay. So whatever hibbity jib I did in order to produce this, you can trust it. So this allows us to write R fully in terms of eta. So all I have to tell you is where you are in the orbit, and you know how far away you are. Right? When I say where you are, I mean how far along in the orbit you are. Okay, so I'm not going to go through this. I will keep them up in the slides so you can do this at home. You can demonstrate this. Maybe it'll be fun. Maybe it'll be a nice reminder. Okay. Here it is. So that's all you need to prove it. Just do that. You're fine. 3 pages. Okay. And notice how I write this. This is what I want to see from you. Okay. Words, some stuff, words, some stuff. That's nice. Okay? Like, not walls about. And see how demure it is? Okay. See how I can read the handwriting? It's like, okay. It's hard for me to read your homework. I'll be cranky and I won't look well on it. All right. Okay. There we go. So here's the elliptical orbit. You know, we can go back to thinking now about the energy per unit mass. The reason why we might want to think about this quantity, energy per unit mass, is let's say you have a really large object like Jupiter. You really don't give a shit about Jupiter's change in orbit, right? We're already using that center of mass system where defining things with regards to the center of mass, using a reduced mass, for example, and you might want to think about the energy per unit orbital, right? So let's even remove the energy of the mass of the moving body cares about. So this should be 1/2 mv squared, but because I divided by m, it's just v squared over 2. And similarly, this now only cares about the big one. Okay. But interestingly enough, I can break this apart into the 2 pieces, the radial velocity component and the tangential component. Okay. That's pretty straightforward. You can express this as, you know, you can write this as the total energy for any orbiting body. If you are not changing your eccentricity, or sorry, if the orbit is circular and r is not changing because the eccentricity is 0, then you get back what you thought you had. This is just the azimuthal or the tangential energy, and this is the radial energy. But if you're not changing the radial distance because you're going around a circle, then that first term is, and you can use them for both. That's right. You can also do the angular momentum per mass. This sometimes is called the specific angular momentum. This is sometimes called the specific energy. So I don't know why they took these names, just whatever. Well, we're stuck with, okay? We've done this for a couple hundred years. If you divide by the mass of the object, it just becomes the specific thing of that thing. So you take L, it even gets its own symbol. Very confusingly, it's H, it's not height. Don't think of it as height. It's the specific angular momentum. And the specific angular momentum is actually quite important when you start thinking about multi-body systems. So when we start talking about asteroids and you're thinking about how they're orbiting, you're probably thinking in terms of H, because that's just V times, the tangential V times R. Now, how did I step through there and jump? Okay. Remember, of course, that the angular momentum is a cross product. What's it, the cross product? That's not what I mean by cross product. Cross products in terms of like, what two quantities are being crossed, not the relationship. If I were to write L for the very first time, and I don't think about orbits, don't think about anything, how would you write L? That is one way to write it, but we haven't learned that today.
R cross P.
R cross P, right? R cross P. What is P again?
Density. That's right.
We didn't go home and memorize, right? What did you remember? Momentum, right? The P is silent. Momentum. Okay, so this is R cross M, which is a scalar, V, which is the vector. Momentum. Say that 100 times when you get home. If you don't know this, you're gonna get lost. Because I can't just, define it. P is period, just not here. Right? You're right, you're just wrong. Right? It is the density when it's rho, but not here, right? So you have to be able to know context. And it'll make it so much easier to read and understand in class if you already have an intuition for, oh, I see L, that P probably means momentum. Okay. So let's look here. I have R and V. Okay, for the energy, I have two terms from the fact that the radial component and the eta component are both changing, but here I don't. So which cross run on? Well, I have a cross product, right? The velocity here is comprised of what two pieces? Right. So I have V R and V eta. Right? And what's R cross R? Zero. Right? Because they're not in the same direction. So there is no angular momentum from the velocity along the radial direction. Simple? Okay. So you can follow that. That gives you what I expected it to give you. I wrote it. And you get the R squared everything else. Okay. Let's see if I want to go into the next slide. How bad is it? Oof. Okay. Learn things. Okay. Study the things. Reread the book then. Grab the 2500, crack it. Memorize the things that I wrote last week. Okay. Questions, comments, concerns? God, where did I put my mouse?